Have you ever sat in a park just watching a child on a swing? Back and forth, back and forth. There's a calming, predictable rhythm to it, isn't it? Or perhaps you've glanced at an old grandfather clock, its pendulum marking time with a steady, hypnotic sway. You might have even plucked a guitar string and watched it blur into a vibration, producing a pure, clear note. In each of these moments, you were observing one of the most fundamental and elegant patterns in the entire universe. This calm, regular, repeating motion has a name: Simple Harmonic Motion, or SHM for short. It's a beautiful dance that nature performs all around us, from the microscopic jiggle of atoms to the vast orbits of celestial bodies. This essay is a promise to you. We're going to demystify this concept, stripping away intimidating mathematics and starting with simple intuition. We will begin by just looking and thinking about how things move. Think of it as a journey. We'll start with the familiar image of that swing in the park, building understanding piece by piece. Let's go back to that child on the swing. Imagine the swing is perfectly still, hanging straight down. In this state, it's balanced. It's content. Physicists have a special word for this state of perfect balance: equilibrium. It's the home base, the central point where the object would happily stay forever if left undisturbed. Nothing is pulling it one way or the other. All the forces on it are perfectly canceled out. The magic begins the moment you introduce a little push or pull, disrupting that peaceful equilibrium. Now imagine you pull the swing back and hold it there. What do you feel? A gentle but persistent tug. That's gravity, trying to pull the swing back down, back to equilibrium. The further you pull the swing away, the stronger this backward tug becomes. That pull, the invisible hand guiding it home, is the restoring force. It's the heart of simple, harmonic motion. It only ever wants to bring things home. This gentle corrective nudge orchestrates the back and forth rhythm. Once you let go, the restoring force takes over. It pulls the swing back toward the center. But the swing doesn't stop at equilibrium. Why? Because it has built up speed on the way down. It has momentum. So it overshoots and swings up the other side. Gravity pulls it back, slowing it until it stops at the peak. Then the process repeats. Smooth, continuous, predictable oscillation, a pull towards center and an overshoot from inertia. To really get a feel for this, let's solidify our understanding with two classic perfect examples: the pendulum and the mass on a spring. First, the pendulum. It's just a weight, a bob, suspended from a fixed point by a string or a rigid rod. Pull the bob to one side and release it. Gravity provides the restoring force. A component of gravity pulls the bob along its arc toward the lowest point, the equilibrium. For small swings, it behaves as nearly perfect SHM. Swap the swinging bob for a bouncing weight. A metal spring hangs vertically. Attach a small weight. It stretches and settles to a new rest, the equilibrium. Upward spring force balances downward gravity. Disturb the balance. The stretched spring pulls up as a restoring force. The mass accelerates through equilibrium and overshoots. Above equilibrium, it becomes compressed and pushes downward, slowing and reversing the motion. Different mechanisms, gravity or elasticity, yet both yield smooth, repeating oscillations around equilibrium, governed by the same math. These are our Rosetta Stone for SHM. There's another equally beautiful way to look at simple harmonic motion, through the lens of energy. Motion isn't just about forces and positions. It's also about a graceful exchange of energy from one form to another. The two main characters here are potential energy and kinetic energy. At the highest point, the swing is momentarily still. All energy is stored as gravitational potential energy. As it swoops down, it loses height but gains speed. Potential converts into kinetic. At the very bottom, its speed is greatest. Almost all the energy is kinetic. Then climbing up, it slows. Kinetic converts back into potential. At the peak again, speed is zero. Energy is stored as potential. This seamless conversion from potential to kinetic and back again drives the oscillation. If there were no friction or air resistance, this perfect exchange would let the swing move back and forth forever. Now that we have a strong intuitive feel for forces and energies, we're ready for a little language physicists use to describe this motion. I promise it's more like a secret code that elegantly summarizes everything. xt, t, a cos, ot plus ef. xt is the position at time t, the answer we seek. Is it left, right, or in the middle right now? That's xt. A is amplitude, the maximum displacement, the size of the swing. Cosine is a natural wave pattern. Multiplying by A scales it to our motion. O, the angular frequency, tells how quickly it oscillates. Large O is fast and buzzy. Small o is slow and gentle. T is time, simply ticking forward. F, the phase, tells where in the cycle we started at t = 0, peak, middle, or in between. Together, the equation gives the size A, the speed O, and the start F, predicting position X at any time t. It's a wonderfully compact piece of poetry describing a dance. Let's make this concrete with our trusty pendulum. One of its most useful properties is its period. The period t is the time to go all the way out, all the way back, returning to the start. For small swings, this period is remarkably consistent, perfect for timekeeping. We can calculate it simply. T equals 2 pi times the square root of L over G. L is the pendulum length from pivot to the bob's center. G is the acceleration due to gravity, about 9.8 ms2. Notice what's missing, the mass of the bob. Same length means same period regardless of weight. A long pendulum swings slowly, a short one quickly. Length sets the tempo. For L01M, T2P198, 2.1 s, about 1 second out, 1 second back, the seconds pendulum. This simple relation underpinned the earliest accurate clocks. The steady beat of SHM isn't just academic, it powers crucial technologies. Pendulum clocks, pioneered by Christian Huygens, counted precise swings to track seconds, minutes, and hours. Clock running fast? Lengthen the pendulum. Slow? Shorten it. This precision revolutionized navigation and daily life. Modern phones contain accelerometers, tiny masses on spring-like structures. SHM on a microscopic scale. Measure frequency and amplitude of tiny vibrations, and the phone knows its motion. Quartz watches use crystals vibrating at ultra-stable frequencies, a form of SHM, counted electronically for accurate time. From airbags to synth tones, restoring forces and stable oscillations quietly run our world. Different scales, same principle. The universal language of oscillation. We've journeyed from a swing to a smartphone. A back-and-forth motion governed by a gentle pull to center explains so much. SHM is arguably the most important motion in physics because almost any stable equilibrium, nudged slightly, behaves like a simple harmonic oscillator. In solids, atoms vibrate about fixed positions, essentially SHM, explaining heat capacity and sound in materials. A wave travels while the medium oscillates. Air molecules and sound waves oscillate around equilibrium, SHM again. Even light is oscillation. Electric and magnetic fields dancing. Engineers compute natural frequencies, forms of SHM, to avoid resonant amplification from wind or earthquakes. Respecting SHM keeps our structures safe. SHM is a fundamental pattern woven into the fabric of reality. The best way to truly understand physics is to see it and feel it for yourself. You need a string and a small, heavy object. Keys, a metal nut, even a mug. Become Galileo in your living room. Tie it securely. Hang it from a doorknob or sturdy fixture, or hold the end with your arm outstretched. Let it come to rest. That's your equilibrium point. Measure from suspension to the weight's center. Try about 0.25 meters, a quick, easy-to-time period. Pull back a small distance and release gently. Don't push. Count 10 full swings to reduce timing error. Start the stopwatch at the first bottom pass. Stop at the 10th. Divide by 10 to get the period T. Now compare with physics. T daus 2p Lg. With L, Gauss 0.25 n Gauss and G Gauss 9.8 mm S2. T is about 1.0 s. Try a longer length, you'll see a longer period. You're not just confirming an equation, you're experiencing the elegant, predictable rhythm of nature.